Oh, sure.
I think he's recording now.
Yeah. So,
Oh, let me do a brief introduction for you.
sure.
Okay. Hello, everybody. So I think this is the last talk of this semester. So we will have other talks during the summer and the next fall, the coming fall. But this time, Entropy, Ceyu is gonna give us a talk. And Entropy is a Ph.D. candidate at Duke University. He received his bachelor's degree from the University of California, Irvine. His research focuses on building better computer architecture with the help of machine learning and build a better computer architecture for large-scale artificial or intelligence models, which is the machine learning for ARC and ARC for AI. Okay, take it over.
Thank you. I think we can just get started, right? Yeah. Good afternoon, everyone. It's truly an honor to be invited to this computer architecture seminar to share my research about machine learning assisted hardware design. Today, my topic will focus on one of my recent projects called SNS, which stands for SNS is not a synthesizer. To give you some background information, a synthesizer is a software program that's part of the electronic design automation toolchain, the EDA toolchain, and it converts hardware designs to its corresponding logic gate implementations. As the name of this project suggests, we are not trying to build yet another hardware synthesizer. Instead, we are trying to build a deep learning-based predictor that directly predicts the synthesizer result, which typically includes the power, timing, performance, and area of the hardware. I think I will split my talk today into 3 sections. In the first part, I will provide some background information about what a typical hardware design and implementation flow looks like, as well as share with you about my opinion about why hardware development nowadays is so hard. Then I will explain in detail how the SNS works and how it can accurately predict the hardware synthesizer result at over 1,000 times faster speed compared to traditional EDA tools. Since there are 2 versions of SNS, the V1 model and the V2 model, I will also cover the changes we made throughout our investigation. And at the end, I will share my ideas on how the SNS model can be applied to future researches and how can the SNS model help us build a large language model era design methodologies for hardware development. When I was in early days of my PhD, one major question I had was, why do people hate developing hardware so much? People always say that developing software is nice and clean, but when you work with hardware development, suddenly you have to deal with all sorts of messy implementation details. To give an example, this is the life of a typical software developer. You write your Python code, you give the code to a Python interpreter, and then you press enter and bingo, you got the correct result. Clean and simple. But for hardware developers, life is not as easy. Hardware development involves way more steps than software, and it is intrinsically a harder problem than software developer. Because in today's software, you are only dealing with a time division CPU model, which means that the programmer only need to care about what's being executed sequentially. However, there are way more degrees of freedom that hardware developers have to care about. For example, a typical hardware development process often begins with an architecture design in mind. Then RTLs, usually written in hardware description languages like Verilog, need to be implemented for this specific architecture. After that, simulations need to be run to test the correctness of the hardware design. And we are only halfway through this process yet. After we have freezed the RTL, the circuit got implemented into Boolean gates using a process, as we have discussed, called logic synthesis. The logic synthesis process then gives us a netlist consisting of wirings of Boolean gates and basic components. And we call this gates and components the standard cell library. However, to get the chip ready for production, we need to physically place these cells and route their wirings onto a silicon die. And this process is called the placement and route process. Throughout each of these processes, there are tons of design choices we have to make, and we heavily rely on the feedback of consecutive steps to tune our design of previous steps. As you can see, this means that not only is the whole hardware design flow super complicated, but people also need to loop through this flow many times to get the most optimized design. To make things even worse, these steps are extremely slow. We take the logic synthesizer process and the placement and root process, for example. If we go one layer deeper into the stack, one will find there are many small steps involved. A lot of these steps requires the computer to solve very hard optimization problems. For example, the Boolean optimization, the placement, and the routing. A lot of these steps has proven to be NP hard. And to illustrate how slow these processes are, we did an experiment in which we ran the whole implementation flow for a single core rocket SoC, which takes about only 1 millimeter square using a 7 nanometer technology node. This whole EDA design flow takes around 3 days to run on a decent and fast server. Considering nowadays companies like NVIDIA and AMD are designing chips with over 1,000 millimeter square area and even with more advanced technology node, this slow process has become one of the biggest challenges in hardware development industry nowadays. To put it in a simple way, the experience of a hardware developer nowadays is like you write your code, you run it, you compile it, you wait for 3 days, and the compiler tools tells you there's a fatal flaw in your code, and you have to redo everything again and again. I mean, this is not entirely a bad thing if one wants to have some formal reason for constantly taking breaks, though. But if we take a historic perspective, we know that the density of transistors that humans can bake onto silicon dies is increasing exponentially. In the 1980s, people could only put a few thousand transistors onto a chip. And nowadays, extremely large-scale chips with over hundreds of billions of transistors have been manufactured to support applications like large language model inference. Both the tool chain were used to build such extreme scale, but the tool chains we used to build such extreme scale chips are still the same as when people were dealing with chips with only a few thousand of transistors. For example, VHDL was invented in 1980. Verilog was invented in 1984. And Synopsys, the company that builds all these EDA tools, was founded in 1986. These old tools are still the key ingredients of modern chips that powers GPT-4. So I think another big reason why hardware development is so hard is that the tool chains we use are just so obsolete. There is an over 40 years gap between our design methodology and the tech, the scale, and the application we are dealing with today. I believe solving these challenges we have discussed in hardware design methodology is more important today than ever before. Not only because now human beings have the technology to integrate hundreds of billions of transistors onto a chip, but also because next-gen AI models, like the GPT-5 maybe, demands the next-gen hardware at an even larger scale to be designed. And to design next-gen extreme scale chips, we need the next-gen methodologies. And in my research, I believe the key method for building the next-gen design methodology is to get help from the next-gen machine learning model and artificial intelligence models. So SNS is the model that's motivated by this slow logic synthesizer process and tries to solve this problem using the help from machine learning models. The key idea of SNS is that a lot of the time, the developers need feedback to fine-tune their design to get better results. However, these feedbacks require us to run through the whole EDA implementation flow, which, as we have shown before, is extremely slow. But a lot of the slow optimization that the EDA tools perform are redundant if the developers just want to get feedback, such as how large the circuit is, how hungry the circuit is, and what frequency their circuit can run at. They only need these numbers as a feedback. They don't need the whole circuit to be implemented to every detail. And SNS try to remove all these redundant steps by using deep learning models to predict the synthesizer result directly. And our experiment have shown that SNS is able to achieve a decent accuracy prediction at the speed of over 1,000 times faster compared to existing EDA flows, like the Synopsys Design Compiler. And there are mainly 4 steps of our SNS prediction flow. First, we turn the input hardware code into a graph intermediate representation. Then we sample circuit passes from the circuit graph. With the circuit passes, we can then predict the physical characteristics of each pass using a model we call the circuit formal model. Finally, we aggregate the physical characteristics of each circuit path to form the characteristics of the entire circuit. And this is our final prediction target. To show what our work accomplishes, let's walk through a very small example, a multiply and accumulate unit, or you can call it a map unit. We start with our design on the left, and in this case, we can write it in a Verilog HDL language, right? And it can then be converted into a graph intermediate representation on the right using YOSYS, which is the open source synthesizer suite. And each node in this graph represents a functional module in the circuit, and each edge represents a wiring connection between these modules. Now we have the graph representation of the circuit. We can then start sampling passes. We have one restriction for how we do path sampling, though, that all the paths need to begin and end with either a I/O port or a flip-flop. And in this case, you can see the I/O port is colored in purple and the B flip-flop is colored in green. So for this specific circuit, we can sample 3 paths. The first one, marked in red, originates at the top left 8-bit I/O ports and end at the 16-bit D flip-flop. We record it at the sequence of vertices along the path. And following the same approach, we see another similar path colored in green. Since the circuit can have loops, especially it can have loops from D flip-flops to D flip-flops, which basically is a circuit that modifies this D flip-flop at each cycle, right? And so we also have a yellow path that's looping back to its original D flip-flop. And the intuition behind this flip-flop to flip-flop sampling approach is that by having this constraint, we are effectively sampling the one-cycle passes that encodes the one-cycle behaviors of the circuit, which makes our following analysis much easier. Once we have enumerated the passes, the next step is to predict for the physical characteristics, including power, area, and timing of these circuit passes. But what model is best suited? We could use something simple like a linear regression model, but we quickly run into a problem. Let's consider an example below. If we have an adder and a multiplier arranged in two different orders, the first one will have the adder coming first, and the second one will have the multiplier coming first. Naively, we would assume that synthesizing these two circuit paths will result in identical area, power, and timing, because these paths contain the same functional units. However, the synthesized tools are smart, and they can recognize that a multiply followed by an addition can be optimized into one MAC unit, resulting in lower resource consumption than simply linking together an individual multiply and an individual adder unit. But the issue is that linear regression model cannot distinguish these two passes as they have the same count of different types of functional units. So the linear regressor will always predict the same for these two passes. And more importantly, there are tons of circuit optimizations that this EDA software does. And the SNS model needs to learn exactly how this EDA software performs optimization on the circuit, such that the SNS model can accurately predict the power, area, timing of the final circuit. And that makes the linear regression model not suitable for this task. So to remedy the problem we faced with linear regression, we require a model to consider the adjacency, ordering, and frequency of functional units in a path. This is a similar problem compared to the natural language processing problem, the NLP problem, where the meaning of and the sentiment of a sentence depend on the adjacency, ordering, and frequency of words in a sentence, right? And as you may have all know today, transformer is the model that's frequently used in an NLP field, which is designed to do exactly this. Sorry. Therefore, we designed a model called the circuit formal model based on the transformer model. That is, instead of processing words in a sentence, this circuit formal model processes functional units in a path to infer the path level characteristics of these circuit passes. We make the model much smaller and faster than the original transformer model by pruning the original 100 million parameter transformer model to only 1.4 million. And this model can estimate the path level characteristics at far faster speed than traditional synthesizer and with far greater accuracy than a simple linear regression model. Using the circuit formal model, we can estimate the timing, area, and power of passes in our circuit. But paths are just subcomponents of our circuits. And if we want to have our prediction of the entire circuits, we need another model to merge these results, to aggregate these results together. As it turns out, a very small multi-level perceptron, a very small MLP model is sufficient to perform this inference. And the reason that we don't need another very powerful, very expensive model for aggregating path-level features is that the complex structure and contextual information of the circuit has already been captured and learned by the previous circuit formal model. And the task of the MLP model is simply to aggregate the information inferred from the circuit formal together into the prediction of the global circuit. For our experiment, we reserve half of the data, half of our data set for training and the other half for evaluation. Here we show some of the accuracy results from our evaluation. We measured the root relative square error against the ground truth result and reported in a table. For this matrix, the lower the better. Compared to the prior work, which performs only timing analysis, SNS lowers the error rate. The error matrix for power and area has no direct comparisons, so we can still visualize the quality of our result using the graphs on the right side, which we plot the characteristics estimated by the SNS against the ground truth result. And with perfect accuracy, all these points should lie in the diagonal line. But you can see like the results predicted by SNS is pretty close to this diagonal line. And this suggests that SNS achieves high accuracy for predicting these characteristics. But let's get back one step and think about why we do SNS in the first place. We need it to be fast. And in this graph, we plot SNS execution time as the function of the execution time of the Synopsys Design Compiler. The size of each circle signifies the final die area of the design, and the lighter the color, the higher speed up SNS can achieve for that particular design. We found that at larger designs, when the design is with larger die area, SNS can run drastically faster compared to Synopsys Design Compilers. And for the largest design in our dataset, SNS achieves up to 5,000 times speed up over the Synopsys Design Compiler. And on average, SNS still achieves 760 times speed up over these tools. Notably, this speed up was achieved using only a CPU to perform the neural network inference. If high performance hardware such as GPU is available, SNS can achieve average speed up of well over 2,000 times. So we have shown that SNS can accurately predict the results quickly and accurately for a single design, but how this tool might help in real design workflows. Let's consider another example where we use where we show the use case of SNS. Suppose we are designing a general purpose processor. It could be something look like the open source RISC-V Boom core, which there are many hardware design parameters that we can tune. For instance, we have branch predictor. We need to dictate what's the fetch width, what's the decoder width, and what's the configuration of the memory ports and the memory subsystem. And this list can go on forever. To find the optimal configuration which meets our design goal, we will need to perform synthesize for each and every combination of these parameter choices. And that's prohibitively expensive. So here on the right, we show a table of our choice about some of the most important parameters for the Boom core. And in total, we have the total number of combinations over 2,000. And if we use the existing EDA tools, if we use Synopsys Design Compiler, for example, to synthesize all these designs, it would require a really long time. And based on our experiment, it takes around 45 days on a 96-core server. And instead of waiting a month and a half to figure out which configuration is the best, we can use SNS to quickly perform the entire design space exploration in a bit over 2 hours. So SNS also achieves good prediction accuracy, and we can see its error relative to the ground truth results in the table on the right. And the result of the DSE is plotted at the top left two graphs, where we can see that very clearly a Pareto frontier showing the diminishing single core performance of area and power. As a recap of the SNS model we have discussed, we learned that machine learning models can be great tools for estimating the synthesizer result accurately and quickly. However, we also noted two big problems in the SNS model's training and inference pipeline. The first major issue is that collecting high-quality RTL designs online takes a lot of work. There are not enough sources available. We tried our best and could only collect around 100 high-quality design points. Also, the SNS model is trained with the golden data generated from EDA tools, which means that in order to generate the training set for SNS, we need to synthesize and implement all these 100 design points. And as we have discussed before, this process is really slow and label intensive. Additionally, another concern is that logic synthesizer is not like software compilation, where you give the software compiler code and the compiler emits the binary for you. There are actually many knobs, many parameters one can tune during a logic synthesizer process. For example, you can choose what technology node you are working with. Are you working with 7 nanometer or 14 nanometer or 90 nanometer? You also need to dictate various operating conditions and different optimization targets for your specific purpose. Is your chip going to run at high or low voltage, high or low temperature? And is your optimization emphasize more on the latency or the power or the area of the chip? In order for the SNS model to predict accurately, considering all these parameters, you need to collect one training dataset and retrain the whole model for each possible combination of these parameters, which is prohibitively expensive. And to solve this problem of the first version of SNS model, we developed the second version we call the SNS v2. And SNS v2 emphasizes two things. The first thing is training data efficiency, and the second thing is model transferability. So the pre-processing steps of the SNS v2 model are similar to that of the v1 model, in which we convert the RTL design into a graph representation. But instead of taking a path-based approach in the v2 model, we use a graph-based approach. To be more specific, we built a hierarchical graph neural network model that infers the characteristic of each hardware design based on the hardware design's hierarchy and graph structure. I will explain why we made this change in a moment. But one of the most important innovation of the v2 model is the three-phase training approach, or often called the meta-learning approach. And in this approach, the training process is split into three phases: the pre-training phase, the fine-tuning phase, and the domain adaptation phase. SNS v2 actually learned this approach from large language model training pipeline, such as GPT-4. And in large language model training pipelines, the model is first pre-trained on a large corpus and then fine-tuned to be able to chat with people. And finally, it can be adapted to some specific domains, such as answering math-related questions or write code for you. And usually in practice, the pre-training is done in an unsupervised or self-supervised fashion, such that no label is being provided. I think one very interesting idea of SNS v2 is how it performs pre-training in an unsupervised fashion. Let's take a look at this circuit here. It's one very simple circuit with only one adder in it. Suppose that we mutate this circuit such that we can add a bitwise OR to one of the inputs of this adder, and we basically make this input OR 0 and then pass it to the adder. What will happen is that since we know that any value OR 0 equals to the value itself, right, based on Boolean optimization, essentially we create a mutation with the exact functional behavior as the original circuit, although this mutation has a different graph representation than before. This is very important because we can also mutate this graph such that although the graph structure is the same, but one node in the graph may represent a multiplier instead of an adder, for example, and we got a circuit with completely different behaviors, but with same graph structure. Both of these types of mutations, if we can fabricate these mutations, allows us to learn a general purpose circuit representation model if we apply a contrastive learning approach. This approach allows us to pre-train the SNS V2 model without having to generate any labels using the slow EDA tools. And during this contrastive learning, contrastive pre-training, all we have to do is to generate functional equivalent samples and functional different samples and feed it to the model. And our optimization target would be that we can just force the model to maximize the embedding distance between functional different circuits and minimize the embedding distance of functional equivalent circuits. And after all, this allows the SNS to do a pure unsupervised pre-training based on circuit equivalencies. I will skip the fine-tuning and domain adaptation processes of the SNS V2 model as they are very similar to that of the V1 model. You can always refer back to our paper about more of these details. Here, we present some evaluation results to show the effectiveness of our three-phase training approach and how it enables the SNS V2 model to be transferable across multiple domains. So the SNS V2 model is fine-tuned at the 32-nanometer dataset, which with typical condition callers. Its evaluation accuracy for the PPA prediction is shown here, and it's already much better than the V1 model. More importantly, the model is tuned at 32 nanometer and can be transferred to different condition corners at 14 nanometer with only a few labeled samples as a calibration dataset, while still achieves excellent inference accuracy. This is possible because a nice feature of the three-phase training approach is that SNS V2 decouples the inference of the structural functional characteristics of the circuit and the inference of the physical and mapping characteristics of the circuit. Recall that during the pre-training process, no technology library is specified, and the model has not been exposed to any labeled data, which means that the pre-trained model only infers the structural and functional characteristics, and therefore it can be reused across multiple targets because these targets are physical library specific, right? And what we do in the SNS V2's inference pipeline is that once the functional and structural information has been extracted from the pre-trained model, once we have a good representation vector obtained for the input circuit, predicting a technology library specific and condition specific PPA result for the input circuit becomes a much easier task. And that's the reason why we can adapt to another domain with only a few samples to calibrate the model. So we have discussed the two versions of SNS model. A good news is that a startup company called Ceyu is building an industry-grade real-time PPA predictor based on some of the ideas of SNS. I think this proves that the industry demands such a product like SNS, and such a product can really help speed up the overall hardware development process. But I think, after all, the PPA predictor is only really a small portion of the next generation hardware development methodology. I believe more AI-assisted automation tools and approaches need to be built, and the circuit representation learning approach proposed in the SNS V2 model can be part of this process. In the future research, I think I will work on one more interesting use case of the SNS V2 model, which is that we can use SNS V2's ability to represent circuits in a high-dimensional space to build up a knowledge database for RTL circuits. For example, as shown in this figure on the right side of the slide, we can collect some well-designed, well-implemented RTL designs and obtain the representation vector of each of these designs. And we can also predict the PPA for them at the same time. And all these results are put into a vector database with the index key being the representation vector and both the RTL code and the PPA results of the circuit being stored as values that's like linked with respective keys. The reason why we need a vector index knowledge database like this is that it could help large language models generate better RTL code. Large language models nowadays are good at generating code, but I think there are two major problems, especially two major problems for hardware designs. First, the generated code is not guaranteed to work, and you don't have any method of to verify if the code really works. Second, if the code is correct, if the generated code is correct, or if you don't even care about verification, the LLM also does not have the knowledge of generating optimized code. And this is very important for hardware designs. And if we cannot achieve these two goals, generating RTLs using large language models is going to be disastrous for the hardware field. I honestly don't have an answer right now to how to solve these two problems, but I believe a retrieval augmented generation, or so-called the RAG, could be something that makes these two problems a bit easier, at least. So a retrieval augmented generation, an RAG, is an approach that lets the LLMs, lets the large language models copy humans' homework. Suppose we have we prompt a large language model to design as a CPU core. With RAG, the LLM does not have to start from scratch. It could query the knowledge database and retrieve some of the already existing CPU core designs. And it could modify these designs incrementally until it fits the need of the user's request. The LLM could also query subcomponents of a CPU core that has already been verified by human engineers. For example, a CPU core requires an ALU, and the LLM could just retrieve the ALU design in the knowledge database and use it as is, as a black box. That's in that case. And if we have already verified black box in our design, we just don't have to verify it again, which saves our work. My long-term goal is to create a suite of tools for LLM-assisted hardware development, like a Swiss Army knife. First of all, I think what's being stored in the knowledge database, knowledge vector database, should not be limited to the RTL circuits only. Other important knowledge sources, such as documentations for EDA tools and RTL languages, could also be included. The function of the large language model is also applicable to way more tasks than just generating code or predicting PPAs. We could also add chatbots and EDA automation agents that controls the EDA and do tedious implementation jobs without any human intervention. I think of this figure as a glimpse of what the future hardware development tool chains will look like. And I believe as AI is getting better and better, and more researchers getting interested in this field, we will see more amazing AI-assisted tools being built. And I think that concludes my presentation. You are more than welcome to ask me any questions online, and you can also refer to our paper for more details. And if you prefer like offline questions, I'm also happy to answer like email questions. Thank you.
Thank you, Entropy. It's a very interesting talk. And I think now we can have questions from online audiences. Feel free to throw your questions.
Yeah. Hi, this is Kai speaking. I'm the new guy in UMM Morris. So first of all, wonderful talk and amazing computer architecture seminar series. I have one quick question. That is, how is the generalization of SNS and SNS V2? In other words, can the pre-trained deep learning-based predictor be used to predict some other downstream tasks beyond power, performance, and area?
Yeah, so you're talking about like this contrastive learning approach, right? To make sure I understand your question correctly, you mean that did we try other downstream tasks than just predicting the power, area, and timing of the design?
Yeah.
We tried in during our investigation process, but we didn't put it onto the paper though. We did try some other interesting stuff like hardware Trojan detection, right? I think this model could be a perfect base model for the task of hardware Trojan detection, because this embedding model is basically learned with circuit equivalence, and it's able to predict for equivalent circuits, and that's how hardware Trojan detection works, right? And we also tried some other power, area, and timing prediction tasks that's not specific to ASIC, right? We tried to predict the placement and route result directly, but that seems to be such a challenging task that's we didn't get a very good result there. But we also tried to predict for FPGA results, which also works.
Yeah, Wonderful. Yeah, thanks again for the talk and the computer architecture seminar series.
Thank you.
Yeah.
So I have a quick question, very interesting talk. I have a quick question about your first work, right? It seems like how do you guarantee the scalability of your model? Right? From my personal point of view, it's like the size that you can input to the MLP model is your input size, right? And which is your circuit size. So how can you guarantee the scalability of your model?
I think that's a very interesting question, and that's exactly the reason why we do this. If you can see here, why we do this path sampling approach. The reason that we want to do path sampling is that the circuit could be very large, right? If we want to represent the circuit in a graph, it could consist of millions of nodes, and as you may have heard of, like millions of nodes of graph, a graph of millions of nodes is really hard to deal with. And if we can extract passes from them, because paths are just 1D, right? And it's really easy if we can train a good model to predict the physical characteristics of these passes, right? So I think the idea of the scalability, the main idea of scalability here is that we want to do as much work as possible locally for circuit passes. And we want to do as little work as possible for aggregating these results. Right? Does that answer the question?
Yes, but sometimes if we find those like timing issue, right, we can insert some latch or between those gates, right? So how do you detect those things? I mean, in your model.
I'm sorry.
So if you have a timing issue, right? So sometimes we can insert some whatever the what the latch, right, between those logic gates, right, to optimize the latency. So how do you capture those components in your model?
I think first of all, the purpose of SNS, all it does is to imitate the results generated from EDA tools. I mean, if this EDA tools knows how to optimize it, SNS learns how it optimizes it, even though SNS doesn't do the optimization itself, right? It's just a neural network model, right?
Okay.
And the second thing, I think a second point is also very important because when you have a timing prediction for the circuit, says that SNS tells you that your circuit doesn't pass timing, then what it really cares about is where is the critical path is in your circuit, how you should modify your RTL such that it meets timing next time, right? And I think that's another advantage that the path-based sampling approach provide us with. So with path sampling approach, we know the timing of each circuit path. And if we're lucky enough, if we happen to sample the exact critical path, right? We know that critical path is going to cause us trouble, and we can just tell the user where the critical path is so that the user can fix their RTL.
Okay. Thank you. Yeah.
Thank you.
So any other questions?
Yes, I had a question about SNS version 2. So the part where you do the hierarchical graph and then you just do the prediction based on the hierarchy of the smaller subgraphs that you made.
Yeah.
So for the contrastive learning, it requires the two entities that are being contrasted against, they should match in the same size. So I might have two subcircuits that might do the same thing, but they're different in size and everything. So how do you justify that? Or how do you make sure the prediction on the timing does not violate the real output because you missed this fine-grained information on the subgraphs?
Yeah, that's also a very good question because that's exactly the portion that I omitted in my talk for the SNS V2 model. To give you some more details about how we actually implement this, if we look at this hierarchical GNN, right? If we look at this contrastive example we provided, we are working with very, very small circuit paths, right? And that's the first level of the hierarchy in our hierarchical GNN. And we have a similar idea compared to our SNS V1 model that these circuit partitions, at the first level, we work with small circuit partitions, right? And we have one restriction that all these circuit partitions need to be DAGs, need to be direct acyclic graphs. and the top layer and the bottom layer of this DAG, again, need to be I/O ports and registers so that we can capture the one cycle behavior of the circuit. I think this really is the key idea of SNS, that we are dealing with RTL circuits, and RTL stands for register transfer level circuit, right? And we are capturing this register transfer level behavior just based on our mechanism of doing either path sampling or graph sampling, right?
Okay.
So
yeah, thank you.
That's right. In the contrastive learning, we are only dealing with DAGs that's within one cycle. Yeah.
And do you use any form of pooling to make sure the vectors that you're contrasting are the same shape, or what is the process at the end that you learn each subgraph?
So the way we implement this is that we basically ported many circuit equivalent transformations from the Yosys tool suite and the circuit framework, right? So those two are like compiler frameworks for EDAs. And in these two projects, we can find a lot of these transformations that preserve the circuit's functionality. And we can just apply these transformations onto our circuit graph such that we have a mutation.
Okay. Yeah. Thank you very much.
Thank you.
Great. Any more questions? If no, I have a question.
Sure.
So my question is, it seems that you mentioned this framework is trying to capture the registers to register one cycle thing. So I'm wondering, is it able to, for example, give it a more higher level description of the whatever schematic or diagram and make it in a way that it works for high level functions rather than just very simple register level?
I think right now, all it does is nothing above the RTL. First of all, it's not doing anything higher level than the RTL, but it is able to extract features that's higher level than one cycle, right? Because otherwise, how are we dealing with multi-cycle circuits, right? And the way it does is that because we have this partition mechanism where we obtain a large circuit with whatever number of stages, we can partition this circuit into small circuit partitions, and we can predict the characteristics of each of the small partitions. And then we can like analyze the distribution, analyze the portion like each circuit subdivision is contributing to the entire circuit, right? And that gives us like a, that allows us basically to generate like an area or power pie chart for the entire big circuit.
Okay, cool. Any other questions? If no, I don't have questions anymore. So let's thank the speaker again. And yeah, I think that's the end of today's talk. It's a really interesting one. And later I will post the video online and share the link with a speaker, as well as post it on LinkedIn so that more people can see it. Okay, thank you. Thank you everyone for joining, and see you next time. Thank you, Ceyu. Bye.